Hello, everyone. Welcome to lesson 15 of Calculus 1. So this is probably one of the most important lessons, not only in this course, but all throughout calculus. This is going to be a rule that we're going to be using all the time. And it's good to think of it as sort of the glue that holds all of the other derivative rules together. This rule is called the chain rule. This is definitely the most important derivative rule that we're going to learn. All right, so we've learned how to do the derivatives of a lot of functions now, and in last lesson, we learned how to do the derivative of trig functions as well. But what happens if we have an amalgamation of some of the functions that we've learned about? So for example, let's say we wanted to do the derivative of cosine, but instead of just x, we have x squared plugged in. Now it might seem like, okay, well, we just do the derivative of this and then maybe plug in the derivative of that. But unfortunately, it's not that simple. So even though we know how to do the derivative of cosine, we know how to do the derivative of x squared, we don't yet know how to do the derivative when x squared is substituted into cosine of x. What do I mean by substituted? I'm talking about function substitution. Let's say f of x, let's call it cosine of x, f of x, and g of x could be x squared. Then if we want to write this function, the way we would do this with our function notation is write f and then have a little circle and then g. And this would give us cosine of x squared. This indicates that whenever we see an x in our f function, we replace it with a copy of g. So instead of this just being a normal x, we replace it with an x squared, as is written here. Now let's say we wanted to do the derivative of this. So why don't we call this new thing big F, because this is a lot of stuff to write every time. So this is big F of x. And let's say we want to know f prime of x. That's the question we're trying to answer. We're trying to get the derivative when we have one function plugged into another. And this is where the chain rule comes in. So the chain rule states if big F of x is the composition of two other functions, and both f and g are differentiable, meaning we can take the derivative of each of these separately, then if we want to do the derivative of their composition, we first take the derivative of what's called the outside function, the function that's having something plugged into it. We take the derivative of that, but we keep whatever was plugged in there, plugged into it, even after we do the derivative. Then we multiply by the derivative of whatever was plugged in, or the inside function. So that's kind of how I like to think of it. This is our outside function having something plugged into it, and this is our inside function here. So what we do is we take the derivative of the outside, keep the original inside in there, and then we multiply by the derivative of the inside here. All right, so I want to write this in another way. So we're using prime notation here, but we could also write this in Leibniz notation. I think it's actually pretty enlightening to do so. So let's say that y, let's call y f of x, or sorry, f of u. U will be some kind of third variable here. And then u in turn is g of x. So if I substitute in g for u, which it is, I have f of g of x. Then if I want to do dy dx, that will be dy du times du dx. And here you can see that du dx corresponds to this, and dy du corresponds to this. dy is taking a derivative of f, but then we do it with respect to u. So we keep our original u, or g of x, plugged in there. And then we do the derivative of g of x. And you can see why this equation might be true, because if we imagine these for a moment as fractions, you can almost cancel out these du's, and then we have dy dx left over. Here's one more example to kind of show you why this is true before we start using it. So let's say we're in a car, and this car, the car's tire is spinning at 2,500 revolutions per minute. So it's spinning around 2,500 times every minute. And now let's say that every minute we go, oh, sorry, I meant revolutions per mile. Sorry, revolutions per mile. And then let's say we go 1.5 miles every minute of driving. So this is actually pretty fast. This is 90 miles an hour. So what we want to know, our question here is how many revolutions per minute will we have? So we know how many times it spins when we go a mile, and we know how many miles we go in a minute. So we can use that information to give us revolutions per minute. So it turns out that if we do 2,500 revolutions per mile times 1.5 miles per minute, we see that kind of like this canceling right here, we have a canceling of units right here, and then we multiply, and we end up getting 3,750 revolutions per minute. So we use these two right here. This is very similar to the chain rule. Whenever you have two rates of change and they have 1 unit in the denominator, 1 minute in the numerator, the way you combine them is you multiply them together. And we do some unit canceling, and then we get what we want. So we multiply so long as we have the same unit on the bottom as we do on the top here. This is kind of to bring it back to earth here. Usually, once we kind of get in the rhythm of it, we take the derivative of the outside, plug the inside in, and then we do the derivative of the inside. And I'll give you guys another way of thinking about this in a little bit. All right, so let's see an example of the chain rule in action. Let's go back to the question that we started the lesson with. Let's say we wanted to do the derivative of cosine of x squared. Okay, well, what we're going to do is we're going to represent cosine as our outside function, and then x squared as our inside function. So remember, the chain rule says that we have f prime of g of x. All right, well, first let's get what f prime is. The derivative of cosine is negative sine of x. So if we have f prime, negative sine of g of x, that means that instead of this x here, I'm going to be putting in an x squared. So we have negative sine of x squared. So that's the f prime of g part. Then we multiply by g prime. Now what's g prime? That's going to equal 2x. We multiply by 2x here. Another way to think about this is you're kind of breaking the function into different layers. You do the derivative of the outer layer first, but then you still haven't touched this inner layer of x squared. And then finally, you get into the inner layer of x squared, which is going to turn into 2x. So we end up with negative 2x sine of x squared as our derivative here. All right, this may be a bit confusing at first, but it becomes clear the more examples we go through. Let's do the derivative of the square root of sine of x plus x squared plus 1. All right. Now, let's identify what our outer function is. So we have the square root going over this whole thing right here. So it seems like our outer function is the square root of x. And then what do we have put into that square root? It seems like sine of x plus x squared plus 1 is what we're sticking into this square root right here. So this is how we decompose our function. Okay, now that we've identified the two pieces, let's go ahead and do the derivative. So if we do the derivative of the square root, remember the square root function is x to the 1/2. So we could do the power rule, and we get 1 over 2 x to the 1/2. Because remember, we lower the power by 1, so it'll be negative 1/2, so a 1/2 on the bottom. And if we'd like, we could also write this as 1 over 2 root x, because x to the 1/2 is root x. Okay, so how does that translate? So this is all sort of separate here. How does that translate to our original problem? Well, we do the derivative of the square root, and we have 1 over 2 with a square root. Rather than just putting x, remember, we have to have the original inside, what we plugged in here originally. So we have sine of x plus x squared plus 1 right here. All right, now we're not done. So that's the f prime of g part. Now we need to multiply by g prime. Okay, so g prime here, the derivative of sine will be cosine. The derivative of x squared will be 2x, and the derivative of 1 will just be 0. So we're going to multiply by cosine of x plus 2x. And usually chain rules are a little bit messy once we're done with them, so let's clean it up a bit. We end up with this right here. Write it as one fraction. There we go. That's another example of the chain rule in action, this time with a square root right here. All righty. Let's look at another example. This is definitely a rule that's best learned through practice here. All right, let's combine the chain rule with some of the older derivative rules that we've seen. So let's say we have x times e to the x squared right here, and we want to take the derivative of this. Now, one thing I want to go into before I do this problem, this is a common misconception. E to the x squared is not the same thing as e to the x squared without a parenthesis. Because the way these are different is that if I use my exponent rules here, I have a power then raised to another power, I multiply the power. So I get e to the 2x for this one. I think it's pretty clear that this would not be the same as actually putting an x squared into the exponent. So for example, if I plug in x equals 1, this will be e squared, but then this will be e to the 1 squared, which is e to the 1, which is e. I want you guys to be careful about this. Don't just rewrite this as e to the 2x. All right, so with that out of the way, let's go ahead and try this. Now, if we're doing the derivative of two functions multiplied together here, so we have x, and then we have e to the x squared. So we have two functions multiplied together, meaning we're going to need to use the product rule. Okay, so I'm going to do the derivative of x first, giving us a 1. Then I leave that e to the x squared alone. Then I'm going to leave the x alone, and I'm going to do the derivative of e to the x squared, which I'll just write like this for now. So this means I'm still going to have to do the derivative. All right, so then that means that all I need to do is use the chain rule for this part. Okay, so what is my outside function here? If you see something inside the exponent of something like an e, or perhaps a different number, it turns out that e to the x is our outer function, and then whatever is in the exponent is the inner function, because we're taking this x squared and sticking it in the exponent here. This is what we're going to be using to do the chain rule. So we know we're going to have the derivatives of both of these when we use the chain rule, so we might as well compute them now. So here are the derivatives of our outer function and then our inner function. All right, let's rewrite this. We have 1 times e to the x squared is e to the x squared plus x, and then let's put parentheses for this chain rule. All right, so the chain rule says we have the derivative of our outside with the original inside plugged in. Now, the derivative of our outside is e to the x, because our original outside was e to the x, and it's its own derivative. So I'm going to put x squared into here. And then I'm going to multiply by the derivative of the inside. So it's going to be times 2x right here. So this is one fact about, here's another note. This is another interesting fact about the derivative of e raised to any function. This will actually just be the same thing times the derivative of whatever was plugged in here. And this is a very common situation that we find ourselves in, so it's worth it to realize this. And this is an example of that. All right, and then I guess we could simplify this. There's technically a 1 times this here and a 2x squared here. So we have 1 plus 2x squared e to the x squared here for our derivative. So we're going to be combining the chain rule with the product rule, and as we'll see in a second, the quotient rule as well. All right, let's move on. So let's say that we have x plus 1 over x minus 1 raised to the 21st power, or the current year. Just a very large number. Okay, now technically what we could do, we could avoid using the chain rule here by putting this power on x plus 1, x minus 1, and then foiling everything out. That would be terrible. So we want to avoid doing that. That's not something we want to do. What we're instead going to do is we're going to use the chain rule to help us here. So what's our outer function? Well, it seems like all of this is substituted in to the 21st power. So it seems like our outermost function is something raised to the 2021. And then our inside function is this x plus 1 over x minus 1. Okay, so now we're accustomed to the chain rule now. We know we're going to have to find the derivatives of these eventually, so why not now? So by doing the power rule, we have 2021 x to the 2020. And then with g prime of x, here we're actually going to have to do the quotient rule. So I'm going to square the bottom, giving me x minus 1 squared. I'm going to bring my x minus 1 up here, and then I'll do the derivative of x plus 1. Derivative of x is 1, and the derivative of 1 is 0, so that's just 1. Then I leave my top alone. It gets a break from having the derivative, and then I take the derivative of the bottom. All right, so there we go. And this is something that we can actually clean up a bit. This ends up just being -2 over x minus 1 squared. Because we have x minus 1 minus x plus 1. All right, now we're ready to use the chain rule. So if we do the derivative here, we have the derivative of our outside, so that's 2021. But rather than just having an x, we have whatever our original inside is. So we plug that into here. X plus 1 over x minus 1, now only to the 2020. And then we multiply by the derivative of the inside. All right, so when we do this, let's see, we have -2 times 2021, so that's negative 4,042. We have x plus 1 to the 2020. But then down here, we have x minus 1 to the 2020 times x minus 1 squared. So we actually have x minus 1 to the 2022. We have this rather bizarre looking derivative, but then again, we started with a bizarre looking function. So that's somewhat to be expected. Anyways, this is another example of the chain rule. And this is an instance where we technically didn't need to use it, but it was definitely within our interest to do so. All right, so there's that example. Next, I want to go over probably a simplified version of this. So let's say we have a function, but then rather than plugging in just x, we have x plus a, where a is a constant. Then let's say we want to do the derivative of this. So what are we going to get here? Well, if we use the chain rule, f is our outer function, and x plus a is the thing being plugged in. So we have the derivative of our outside with the inside plugged in, and then we do the derivative of x plus a. Now the derivative of x is 1, and then the derivative of a is 0. So we're just multiplying by 1 here. But that ends up giving us this right here. So this is actually kind of a shortcut here. If we have a bunch of x plus some numbers appearing in our problem, we could just do the derivative normally and keep x plus whatever it is. So for example, let's say we decided to have x minus 99 raised to the 100th power right here. So since we have just x plus or minus a number, and a could be negative technically as well, then we could use this rule and we could just pretend as if this were just an x. So this is 100, x minus 99 to the 99. Because when we do the derivative of the inside here, the derivative of this inside is just 1. So the moral of the story is if you ever see in your whole problem x plus or minus some number, and then there's the rest of the function, you could just treat this x plus or minus a number almost as a single variable on its own. So I'll kind of write this as like a big X right here, and this is a big X. But that's only for x plus or minus a number. All right. Now, here, in all these examples, we had two functions substituted into one another, but there's nothing stopping us from having more than that. So suppose we had the function sine of cosine of tangent of x, and we want to do the derivative of this. How are we supposed to do this then? Well, what we do is we take turns doing the derivative. So first we do the derivative of the outermost function and then leave these alone. Then we do the derivative of the middle function, leave that alone. And then we do the derivative of the innermost function, and then we're done. So let's do the derivative of this. Well, let's see here. The derivative of my outermost function sine is cosine. And then all of this stuff is plugged into sine, so I'm going to leave that alone. Keep that the same. Okay, that was my first layer. So next I move past the sine, since I'm done with that, and I go to cosine. Now the derivative of cosine is negative sine. I leave that tangent that's plugged in there alone. So this is the cosine layer. And then finally, for our innermost layer, we have tangent. So I do the derivative of tangent, and as we saw in the trig video last time, the derivative of tangent is secant squared right here. The way I like to think of this for multiple functions, this is a good mental image. Think of these as Russian nesting dolls. You could imagine this situation as a situation where we have 3 Russian nesting dolls all containing one another. When we do the derivative of the first, we're lifting the lid off the biggest doll and we're revealing the 2 functions inside. Then we lift the lid off of the middle one, and that's just revealing 1 more. And then we lift the lid off the tiniest one, and then there's none left. So you can imagine this as Russian nesting dolls. Is kind of a good image to have. All right, I want to do 2 more examples here, and I think this is really going to put our knowledge to the test. Because now that we have the chain rule, almost every type of function, with a few exceptions we'll go over in the next video, is going to be accessible for us to differentiate, providing it is a differentiable function to begin with. So what I want to do for this example is I want to find the equation of the tangent line to y equals sine squared of pi e to the root x divided by 2 right here at the x value of 0. So remember, interpretation of the derivative is that it is the slope of the tangent line. So in order to get an equation of the tangent line, we need to know what its slope is. So that requires us to do the derivative. All right, now it's pretty obvious here we have a bunch of functions plugged into one another, but what might not be obvious is which one is the outermost function. So I think it's clear that this root x is the innermost one. That's plugged into this e right here. Then all of this stuff is within a sine, but that sine is actually being squared. So the outermost function isn't sine, it's actually the squaring function, or x squared. So when we do our derivative here, our outermost function is x squared. So what's the derivative of x squared? It's 2x, but rather than putting x, we're going to have all of this right here. All right, so we broke through the square layer. Next, we have the sine layer, then the layer with e and this pi over 2, and then the layer with root x. We actually have 4 layers in this one. So the derivative of sine is cosine, and then we have the inside, which we haven't done the derivative of yet. Okay. Next, we're going to do the derivative of this stuff. Now, the derivative of a constant, pi over 2 times a function, is just pi over 2. So we just keep the constant there. And then we do the derivative of e to the x. That's the third layer. But the derivative of e to the x is e to the x. And then we just plug in this root x here. So this is what I was talking about a little bit ago. We can flip back to it. If you do the derivative of e to the something, you get another copy of it. So that's why we have an exact copy of what we had in here. But what we need to add next is the derivative of whatever was placed in our exponent. So now we need to multiply, and this is our final layer, we need to multiply by the derivative of x. As we saw in the beginning of the video, this is going to be 1 over 2 root x. And there we go. So we've broken through all 4 of the layers of this derivative. So let me recap what the layers were. So the outermost layer is something squared. The second layer is sine of something. The third layer is pi over 2 e to the something. And then the fourth layer is the square root of x right here. We plug this, and that gives us our function. All right, so remember what we were doing here to begin with. Let's see here. So we're going to plug x equals 0 into this. I'm sorry, I think I meant x equals 1. As you can see here, plugging in x equals 0 might be give us a bit of an issue here. Why don't we try x equals 1 here instead? Okay, so we have x equals 1. So y prime of 1 will be 2 sine of, now e to the 1 is going to be e. So we have pi e over 2 times cosine of pi e over 2 times pi over 2e by plugging 1 in there, and then times 1/2 right here. All right, this is a very ugly number. One way you can clean it up a little bit, though, is we have 2 sine cosine, and this is the double angle formula for sine. So this will be sine of 2 pi e over 2, and we can cancel those 2's. And then this will be pi e over 4 right here. All right, so this is about as best we could do with this number. So this is the slope of the tangent line. So now we know the slope of the tangent line, so let's actually put the tangent line together. We have y minus y naught is our slope. So we have sine of pi e times pi e over 4. And then we have x minus our x value, which is 1. The only thing we need to do is figure out what our function's value is at x equals 1. And all we need to do is just plug 1 into here. So we have y minus sine squared of pi e over 2. And then we have pi e over 4 sine of pi e, x minus 1. Yeah, this example went a little bit haywire because I forgot about this right here. So plugging in 1 is a bit awkward for this, but still we ended up with our tangent line. And the main point of this is that we do the derivative to get the slope of the tangent line, and in order to do that, we use the chain rule. All right, one final example here. Also, this is a good example because a lot of times in math courses, they construct examples to be like really friendly, like have really nice numbers. But occasionally when you're dealing with things in practice, you don't have really nice numbers. So this is an example of kind of grappling with some awkward numbers right here. It's a good thing to do now and then. All right, and then our final example here, let's say that y is 1 plus a function squared, and then all of that is raised to the 4th power. And we also know that f of 0 is 1, and f prime of 0 is 2. So what we want to do is we want to know y prime of 0. All right, so that's our question here. Let's see, let's do the derivative of y. Well, it seems like our outermost function, the thing that everything applies or is plugged into, is this 4th power here. So that's our outermost function. We do the derivative of something to the 4th. Bring the 4 down. We keep everything the same as it was. We haven't opened that nesting doll yet. And we lower this to be a cube right here. Okay, now we need to do the derivative of 1 plus f of x squared. Now the derivative of 1 is 0, so we don't really need to worry about that. We really just need to do the derivative of f of x squared. Now, with this right here, we have f of x plugged into a square. So we need to deal with the square first. So the derivative of the square of something is 2 times that something. We have 2f of x. And then we get to the innermost layer, which is this f of x. F of x is plugged into this square, and then all of this is plugged into the 4th. So f is the innermost layer. When we do its derivative, well, we don't have a formula for it, so we're just going to have to write it as f prime of x. All right, and then now we can plug in 0 for everything. We have 1 plus f of 0 squared, and that's cubed, times 2f of 0 times f prime of 0. And then we just plug in the numbers. We have 4. Let's see, f of 0 is 1, and 1 squared will be 1. 1 plus 1 is 2, and then 2 cubed will be 8. This is just 8 right here. All of this ends up being 8. And then I have 2 f of 0, which is 1. This part. And then I multiply by f prime of 0, which is 2. Okay, so let's see here. So we have 32 times 2 is 64 times 2. We end up with 128 for this derivative here. All right, so this is another practice with multiple layers of the chain rule. Now, usually the best way to learn mathematics is by practice, and this is especially true for the chain rule. Make sure you try a bunch of problems with the chain rule because it's by far the most important derivative rule that we're learning here. All right, that's it for this class. Next time, we're going to see how to differentiate a few functions that we've missed so far, despite having the chain rule. So we'll see you guys then.